yeah. So
yeah.
so we're talking about that Nature publication.
Yeah.
Yeah. So the guy did like postdoc there, right?
He
Was
did a
it during
postdoc.
postdoc? Okay.
It was during his postdoc that he was able to work with a couple of other postdocs and probably more other postdocs and other research scientists.
Okay.
And they got some very interesting
data.
This was actually, it was the right timing because they were working on something that has to do with I think cannabinoids and all that.
Okay.
And so a time where legislature was being passed in Canada and North America in general.
Okay, yeah.
And they're able to publish the data they got in Nature, and everything just turned around. Like everything
just from
years of hard work, but that's particular paper applied for a faculty position.
Wow.
Boom, he's a faculty member now with lots of funding in Canada.
Wow.
So sometimes it's quality over quantity, you know. So
that's right. It's and another thing is when you, for example, there was a paper I presented in our lab. That should be, when was it? Some maybe like in March this year or so. So it's very related to the model we are doing, right? But we are doing like a cancer model. They are doing like dystrophy. So the muscle dystrophy, they also have lipid accumulation in their muscle, right? And they did a very, extensive work. Just so by reading that paper, you can get a very big overview.
Yeah.
They did transcriptomics, looking at gene expression. They did lots of staining. They did GCMS, so it was a very big overview, right? So when I read it, it made more sense to me. I even gave it more insight on the things that I can try, right? So that was still something where we're just thinking about, just pulling all of those data together and, targeting high impact factor journal, it makes more sense. Yeah.
Yeah, a lot of times even people read your paper and like your publication, they contact like, hey, I'm interested in this experiment you did. Can we send you samples, or can you send, or we think we can do this with this. Can you send your samples? Let's try, right? And that can even, my prof always says the research is working on right now was not what he actually ventured out into. A lot of times
at the initial start,
initial start. So you should just veer gradually into some new stuff, some new interesting stuff from working with other research scientists, and that like opens new doors. Like the modeling I'm working on right now. When I started grad school, I had the intention of doing modeling for my PhD. Was never in it, but just with a paper that came out, and we saw like a knowledge gap in this field area. Like, in this area, like, how can we approach this? My prof was like, I think there's a model you can use to approach this. Can you learn that model? Be able to get a software from a collaborator. And I just like spent the Christmas holiday trying to figure out the model and writing the protocol for it. Right. Nice, so that's a new skill I've learned just from reading a paper from someone's work and seeing, we can actually build on this. We can, and that's what makes science interesting. Just building on that and moving on and just pushing on.
Yeah, you can. It's very interesting, right? Because someone might try a particular experiment in one model, and you're like, this would be interesting to try in our model as well. One that you already have, an experiment design. So I know when I was doing my master's, though, I was reading papers, but not a lot, because I was focused on the experiment,
getting results,
and then when you not get the result and trying to interpret your data, by then you're going back to read, going back to literature, and then you see that there is a way there's a control you should have added when you were doing the experiment based on publication, because if your design is not really matching like the experimental design that other people have tried that have worked, you have to show beyond the reasonable doubt that it actually works, right? So, but it has changed now during my PhD. I even spend more time reading than actual experiments, because I don't know. I was reading a paper recently. They were doing modeling to study lipid synthesis. You know, it was very, I just read like the paper. I haven't kind of dived into deep, you know, so, but it's really something I'll go back and read the paper because it's really very nice. You know, so new things,
Nice.
new things.
Yep,
You know?
it's trying to stay. That's like science is, you need to stay updated. It's moving so fast. The paper I'm reading right now, the group in the United States, I try to follow, I've made it like something I try to follow their group publication.
Okay. Anything that comes out.
Anything that comes out, because they're in our area, in our field, and they seem to be doing a lot of work and something similar to what we are trying to achieve in our group, you know. So I like to read their papers and see what they are doing, and I actually find it interesting. When I read their papers, I'm like, you know what? A lot of times it gives me this idea of what I can also try.
Yeah.
Sometimes
it
confirms what I'm thinking about.
Yeah,
absolutely. Like, you know,
this
what I'm designing. I'm like, yeah, this makes sense. That means it's nice always to keep track. Then I have similar experience. First year, second year of grad school was mostly how can I get results. So every day in the lab, which is very important to get the results. But I just had to learn that there are times you need to sit down and go through literature and see what's out there, see what's been done.
Absolutely.
See, that saves you sometimes. If someone has done something and said this is not the right way to do it, or this is the result from this experiment, right? You can basically take that and say, okay, I know what to do next based on that, you know. So it helps to actually go through literature and see what's out there.
Yeah, one of the things I learned, you know, sometimes you see people publish a paper and the title would be this and this does not cause this. Probably they were expecting the change to happen, and then it doesn't cause that change. It is very important to also publish those findings. True. Very important, because now we've seen that it doesn't work. Yeah. Right. So it's not just about, you know, even though you present as you know, your paper must not always support like your hypothesis. Yeah. So even though it's opposite of your hypothesis, something to also present other people to, you know, we had a symposium some time ago, that when I was doing my master's. The professor that had the best, you know, because a couple of professors just presented their work. The one that had the best presentation was the one that talked about how they were struggling, you know, how the experiment, they did it and then it didn't work, you know, how they kind of adjusted, you know, and it was opposite of what they thought. It was, everybody just opened, like everybody was so keen to seeing, you know, how the things they did was opposite of the hypothesis. And, you know, because
that's actually what research is like. And you have to come to accept that's where the learning and that's where the learning and growing and the development takes place. Absolutely. And just to add what you said, I think it should be encouraged more in the scientific community. Absolutely. That stuff that do not support your hypothesis should also be published, right? Absolutely. I think it's also a contribution to science knowledge, to the web of science. I think we should encourage that, because we focus more on the storyline that really supports your hypothesis. Yeah, but we don't focus more on, oh, this was not what I was expecting, but this is actually something interesting, you know. Maybe this has taught us something about this, you know.
Yeah, and sometimes you don't have to have all the answers. Like you read some papers, they'll tell you, well, we can't explain this currently, right? So we can kind of, you know, maybe design some more experiments to be able to, you know, have this kind of, you know.
Even with the results we get in the lab, the data we have, we still say we propose, or we based on the data, it is consistent with this. We don't say for sure the data is consistent with this, so we propose, or we suppose, or we suggest, because someone will come tomorrow and run experiments and maybe just one condition was changed, and get different results, and they say, okay, this is what it is. So we propose, suggest. We don't say, oh, like this is what it is, right?
Now, when I was writing my review recently, the same thing that people measured, and then out of 6 papers, theory will say it decreased there. I was looking at how, like, mitochondria, for example, with omega-3 fatty acids. Some papers were saying, oh, it decreased the expression of genes involved in mitochondrial biogenesis. And then about maybe out of the 6, 2 we say an increase, 2 we say there was a decrease, and 1 will report no change. But when I go back a little bit and kind of check that experimental design, maybe a little bit of difference in terms of maybe this one used 50 micromolar of your EPA or DHA, this other one used separate concentration and all that, but it's fine, right? Whatever you see, you just make sure you are as detailed in your protocol as much as possible. Right, so that when people are trying to replicate what you did, then they will kind of find similar things.
Yeah, no, totally agree with you on that.
Sure, sounds great.
Yeah, omega-3 fatty acids. I was watching. Sorry, I'm trying to take into a different discussion now.
Yeah,
I was actually watching a documentary some weeks ago, and we're talking about, this was like more in diet and nutrition. I've been watching a lot of documentaries on diet and nutrition, trying to know what's like really good for you, not just physically, but also mentally, psychologically, just how diet can influence you as a whole. And they're talking about how diet influences you mentally, how it helps you, I'm trying for you the right word to use. Right? Should I use IQ? Anyways, they did an experiment where people who eat healthy, eat foods that contain lots of good nutrients, and stuff like, I actually mentioned specifically omega-3 fatty acids, because we don't make it, we need to get a source from fish oil and all that.
Yes.
Compared to people who eat junk foods, people who eat good who eat foods that are that have good nutrients, actually make better decisions in their day-to-day activities than people who eat junk food. So they actually run experiments to show that eating healthy foods will help you make decisions. One of the experiments they ran, I'll look for the link and send to you.
Okay.
Is they put one person, same person. One day, on the day, he had like veggies and all that, fish and all that in the morning, and they take him to a room and they give him a decision to make, right? Now, the decision he makes, can that be out of his own interest, or can be out of trying to salvage the situation? Or when he eats the unhealthy food, his decision changes. So let me tell you what happened. They give him $10 to share with someone in the room. Now the $10 belongs to him, but the person who he's sharing money with has to decide how much he gets. So the person that is sharing money then decides that he's getting $2, and that person takes $8. Now if he accepts, it will take $2, person takes $8.
Oh my
if he does not accept, if he does not accept, none of them gets any money.
Anything, yeah. Wow.
So if person who drank pop that morning or something, we say that they don't want, because so they lose, the other person loses. The person who has veggies in the morning will say, you know what? If I say I don't want, we both lose. But if I say I want, at least I get $2. We'll say, okay, you know what? I'll take the $2 and you can have the $8.
Yeah. It's very, sometimes people do some kind of clinical research and you're like, this doesn't make sense. But when you look at the experimental design, how detailed they are, when they are designed to experiment, is just very, very fantastic and marvelous, right? So, but even with, one thing about science, for example, now with the compound you're designing now, there are a lot of functions and how it works, that a lot that are yet to be uncovered.
Yes.
So that's why sometimes maybe you are doing a clinical trial, you give someone a drug and then you measure something, and then you just want to, maybe that's not a primary outcome, you just want to measure something else. And then you find something interesting, like, whoa, and then that sparks is an area of question, and then you begin to dive deep, and then great discovery comes out of those things, right? So
you need to keep an open mind when doing research.
Absolutely.
Keep an open mind.
Yeah.
Don't box yourself.
Yeah.
That's what first year we did, box ourselves into what we're trying to do and not pay attention to every other thing that
absolutely
can come out from it, So
yeah, that's the thing. We just want to get, do the experiment, get the result out, and then that's it, But all other onions, part of it, they're very fantastic. And sometimes when you are now, definitely all of the data you plan to do, by the time you finish your experiment, not like all of them might end up entering your thesis or your paper. Some of those ones think, oh, they are not very important. Maybe they now become like the very, the stone, the result you rejected at the early part. By the time you revisit it, like, oh, this makes sense, this, right? So
there's a paper we use like in organic chemistry every day. It's called, if you Google it, NMR impurities. So basically, when we make compounds, do a reaction, we purify, we run an MRO, we see the peaks. We're able to, based on the peaks, identify the protons or carbon. Sometimes you see a peak, you're not sure what that peak is. Like, this peak should not be in here. Why am I seeing this peak in this chemical shift? Now, sometimes the peak is coming from the solvent you use to purify. Maybe you not dry it completely, or it's coming from the flask. It can be from even the NMRO tube. Now, a group, I can't remember what school they are from, did an experiment where they ran NMRO for different common impurities. So they just took solvents like acetone, ethyl acetate, methanol, ethanol, pyridine, etc., and they ran NMRO on it, and they published it. Now, it seems like, oh, is that not a simple experiment? Now, that's what we always refer to. When I run NMRO, I'm always opening that to see if I have an impurity, like in my NMRO. I look at the peaks we've identified by running NMRO for the different common impurities, and I can determine if indeed the peaks I'm seeing are impurities or not. That paper is so valuable to an organic chemist, but the idea is so classical, and not use the word classical, it's so simple, but I love it because now it's so useful, so useful.
Absolutely.
It looks like a simple experiment, but I know a lot of organic chemists use that paper every day in the laboratory.
Nice. It's yeah, it sounds great. It's like you mentioned, just being, because so there was also a mistake that I also made. When I'm doing an experiment, I don't really sit down to think of what am I really, really, really expecting. What am I really, really expecting? I know sometimes I have hypotheses and all that. Okay, then what am I expecting? What is my hypothesis really? I know sometimes we have that general hypothesis, but as we begin to narrow down, there should be hypothesis for each, a mini hypothesis for every single thing you're doing. By the time you finish it and you get your results, and then I the first thing I have to go and sleep, because I don't want to think about. I just go and sleep and then think maybe the following day or the following week, then begin to kind of think about, does it make sense, and then begin to read literature and all that, So what I've learned that I'm doing now in my PhD, before I do any experiments. So I think about, okay, these are the 2 or 3 papers where they've done similar thing, and look at what they found, something similar. So this is what I'm expecting. right? And then if it doesn't work fine, then the question now be why? And that why, you know, sparks up the fact. I think that is the point, that at that point where you're expecting an increase and then you didn't see an increase, and then you begin to think, and then maybe you now discover that whatever thing you're doing was independent of that pathway. It happens through that pathway. So it's
the why is the basic foundation as a research scientist. It's why, and that's where the findings come in. Like every single finding has always been why. Why is my data different from what I was expecting? Or if indeed this happens like the way you want, okay, that makes sense. Why this change? Why that change? Or why does it happen this way? What's the pathway? You know, the moment you take why away from research, then I don't know what you are doing really. You can't take that question away from a scientist. The why is the basic foundation.